Hello there. If you go some 10,000 kilometers away from the planet Earth into the Van Allen radiation belt, and you stick out some antennas to measure electric and magnetic fields, this is how a recorded signal would sound like. So what you hear are the streams of charged particles originating from the Sun that are captured by the Earth's magnetic field. Dynamics that you hear is the complex interplay between the charged particle motion and the time-varying electric and magnetic fields. Now, how do we explain electrodynamic situations like this, in general, is the topic of today's lecture. So we're going to explore Maxwell's equations that in the landscape of physics are an important milestone. Initially, we studied classical mechanics, where everything was explained in terms of material points and forces. Now, electromagnetism forced us to introduce a new concept of electric and magnetic field, adding a completely new layer to our understanding of nature. And thanks to the insights brought by the electromagnetism, we will later discover that we also need to refine our concepts of space-time and material point. So this is the plan for today. We will start by refreshing our existing knowledge of basic electromagnetic concepts by looking into the state of the knowledge at the Maxwell's time. Then we will try to cast equations that describe electric and magnetic fields that you already know into a form that allows local description of electric and magnetic phenomena. Describing locally is a keyword here. Working on that goal, we will introduce a new notation that will simplify our lives considerably, allowing us to write equations more compactly. And the big moment comes when we show a completely new term that Maxwell added to electromagnetism. And we will close by discussing implications of this development. So here is an interactive timeline. You can see all interesting developments and dangerous experiments in your copy of the slides. Now, importantly, in the 18th century, Coulomb, using his torsion balance shown here, formulated his law of electrostatic interaction. And early in the 19th century, Bell and Savart formulated their law of magnetostatics, giving us an equation for a magnetic field produced by constant electric current. Somewhat later, Michael Faraday discovered electromagnetic induction, generation of electric field due to change in the magnetic field flux. Now, in addition to this, Faraday was also a great visualizer, and he promoted use of the concept of magnetic lines at a time when most people were still thinking about material points and forces. Now, all this time, optics was developing independently. Importantly, speed of light has been measured late in the 17th century using astronomical observations, and later in Earth-based experiments in 1849 with this apparatus. So the speed of light was known. There was one important discovery that bridged optics and electricity and magnetism that was made before Maxwell, by Michael Faraday again, who demonstrated the influence of magnetic field on light traveling through glass. And here Faraday holds not a cigar, but a glass used in that demonstration. So now we go to the Maxwell, and we will try to cast these existing laws that relate fields and charges at arbitrary distant points in a local format. To start with Coulomb law, instead of calculating force, let us express electric field strength from charge Q. Electric field depends on other charges we might have around, but it turns out that the quantity that does not depend on all possible charges in the space is electric field flux through a surface enclosing charge in 3D, I drew in 2D. To calculate flux, take the electric field vector at each point on the surface, make a scalar product with the vector surface element, and sum these terms along the whole closed surface. That is flux. Now, interestingly, because field is inversely proportional to distance squared and the surface element is proportional to distance squared times angular element, exact distance drops out, and the result depends only on enclosed charge. Now, this result is known as Gauss' theorem. Try proving yourself that the charges outside the surface don't influence the result. And that makes electric field flux a good local quantity. So what is the local form of this law? We take a small volume, say box. This is a projection of the one side of that box in 2D. When I calculate small flux through the box sides, I take the normal component of the electric field on the right side times the surface area and add flux from the left side, but now with a minus sign, because field points inside now. Similarly, from the top and the bottom side and the third dimension. Now you can rewrite differences in field in terms of partial derivatives like this, and pull out the small box volume factor. From Gauss' law, I know that this is equal to enclosed charge, that I'm writing as charge density times volume, over permittivity. Now take the box volume factor out, and this is the first Maxwell equation. So what is this good for? How do I go back to big volume? Say you have two boxes like this and want to calculate flux through the outside area. You just need to sum their two small fluxes. This is because field contribution from the inner surface, common to both boxes, appears as a term both for the flux on the left and right box, but with opposite signs. So common surface contributions cancel, leaving only contributions from outer sides. So in general, this holds. So let us now take Faraday's law. It states that a moving magnet changes flux through the area of this loop. That induces voltage U in such direction that induced current would oppose change of flux through current-induced magnetic field. Now voltage is actually line integral of the electric field along the loop that makes the edge of the surface. So you know what is actually created is an electric field in space. Wire here just allows us to measure it as voltage. Now magnetic field flux through the surface is by definition this. While the electric field itself depends also on magnetic flux changes elsewhere in the space, the electric field line integral does not change if somewhere else in space, not enclosed by the loop, we have magnetic field change. So try proving this. And this makes it local quantity, good local quantity. So what is the local form of this law? We take a small loop, for example in xy plane, so that the vector surface element is pointing in z direction. Small voltage induced along the loop can be calculated as line integral of the electric field along the bottom edge and add contribution along the top edge, with minus sign now since loop direction and E field direction are opposite. Similarly, we write contributions of the right and left edge of the loop. Now, just as in the previous derivation, we can express differences in electric fields in terms of partial derivatives. We can pull out common surface area factor, and we know from Faraday's law that this is equal to local change of B field times surface area. So take the common surface area out, and this is the second Maxwell equation for you. Two more equations actually exist for the two other components of the B fields that you can derive in the same manner. So what is this good for? How do I go back to the big surface? So say you have two loops like this and you want to calculate line integral along the outer edge. You just need to sum their two line integrals. This is because field contribution from the common side appears as a term both in a line integral along the left loop and the right loop, but with opposite signs. So again, common side contributions cancel, leaving only contributions at the outer edge. Now this so far is easy, except that it is a bit hard to remember the exact order of coordinates in these derivatives. So when Oliver Heaviside was learning on his own Maxwell equations, sitting somewhere in the library of the Literary and Philosophical Society in Newcastle, he came up with the following trick. So let's define their symbol as these three components. Now, if we treat this formula as a vector, applying the same algebraic rules we apply for vectors, we get as a result of a scalar product of del and E field exactly this term, which we have just derived is equal to this. So here is a neat way to write first Maxwell equation. And if we apply vector product of del and E field, you remember how to calculate components. For the z component, we get this, which from the second Maxwell equation is equal to. And if you check the other two components and the derived result, they will match too. So you can write the Maxwell equation as this. Now, in general, these two things are called divergence operator and curl operator. Operator means that it takes a function and gives you another function. It works for any vector field. For example, if you take a velocity field in the fluid, say gas in the atmosphere, divergence of a velocity field gives you scalar function that will be positive if there is a gas expansion or gas source somewhere, and negative if there is local compression or gas sink. For incompressible fluids, say flow of water in the ocean, divergence of velocity is zero. Curl of velocity produces another vector field that detects current loops in the flow. Faster moving around the circle, larger curl. So what about direction? If I have a small test disk on the axis and I put it in the viscous fluid, the direction of the curl gives me the optimal axis to have the fastest spinning disk. And larger the curl projection on the disk axis, the faster the disk will spin. So I recommend you to check this video to see curl and divergence in action in various fields to get better feeling for these operators. Okay, let's go back to Maxwell equations now. There is no such a thing as a magnetic monopole. This is an experimental observation. So if I cut the magnet in two, I get two small magnets, not the north and south pole separately. Indeed, all the magnetic sources we ever discovered behave as loops of current carrying wire, creating closed loops of magnetic field. So without sources and sinks of magnetic field, B field behaves as an incompressible fluid. Hence, the divergence of B field is equal to 0. So that's third Maxwell equation. So now the last Maxwell equation, starting from the Bell-Savart law. So imagine a loop around the wire and then start shrinking it. Think about the magnetic field along this loop. After some shrinking, practically all the contribution comes from a small straight section of the wire, since the nearest curved part will be effectively infinitely far away and have negligible effect. So in this limit, we effectively have an infinitely long straight current conductor. It is a nice exercise to prove that the field in the loop around the wire is then this. Now, while B field in principle can depend on some other currents in some other conductors around in space, line integral around the edge of the surface will depend only on the enclosed current. It is a good local quantity, and you can try proving this. By now we know that we can rewrite the line integral as the surface integral of a curl, and we can express current as a current density. So you might conclude that the final result is going to be this. But there is a problem. And the problem becomes obvious when you look at the charging capacitor. So say we have some constant current charging this capacitor. If I take a loop here in this surface and apply previously derived law, I will get this. Now, when choosing the surface, we need just to keep the edge of the surface fixed, but we can shape it otherwise as we like it. So let's take a surface that doesn't cut through a conductor but goes between capacitor plates. Now the current is 0. So these two results don't match. Now what does change between the capacitor plates is electric field. So if we multiply electric field with the capacitor surface, we get that its flux depends on current change on the capacitor plates. So if we take the time derivative and multiply some factors, we get current again. So maybe the solution is to add this factor. In the first surface, the electric field is 0, so it doesn't change that result. But for the second surface, now we get consistent prediction. Maxwell called this factor displacement current, and this is his final fourth equation. So Maxwell thought we might have missed this term before, and this is what he said. We have very little experimental evidence relating to the direct electromagnetic action of currents due to the variation of the electric displacement, that's the factor we derived, in the electrics. But the extreme difficulty of reconciling the laws of electromagnetism with the existence of electric currents, as we saw it, which are not closed, is one among many reasons why we must admit the existence of transient currents due to the variation of displacement. Now, their importance will be seen when we come to the electromagnetic theory of light. So, in other words, it looks like a good term, but we have to look at predictions to check its validity. So let's look at predictions now. Okay, let's consider the following situation. We have two infinite charged planes with equal charge density magnitudes but opposite charge sign. We place two planes next to each other, so density of charges is 0 everywhere, no electromagnetic fields at the start. Now what happens if we start moving the positively charged plane up and down, like shaking it? So if we introduce a coordinate system like this with x and y in the plane and z out of the plane, due to shaking of the plane up and down, we will have some current density of the form. Additionally, we will use these two Maxwell equations. Due to current in the plane, we expect that there will be a magnetic field in the vicinity of the plane. We can calculate that field by taking a loop in the yz plane like this. We can press the sides of the loop infinitely close to the sheet and therefore make any contribution of the electric field flux negligible. And then using equation 3, we obtain that the magnetic field just next to the sheet surface is equal to, and this is the first important result. Now, if we take partial derivative of equation 3 and substitute equation 2, we obtain this. Since the problem is completely translationally symmetric in x-y direction, there can be no variation of the electric field along x and y directions. Hence, these two don't contribute anything. Now, since current is directed along x direction only, we have no other initial fields or sources. Only the electric field along x direction can be non-zero. And in free space where there is no currents, for example, to the right of the plane, we get wave equation with solutions. Now, where wave velocity is equal to whose numerical value, Maxwell confirmed, was in agreement with experiments for the speed of light. So nowadays this is taken to be by definition, like in definition of the meter. Now, with no other initial fields in the space above, we will be interested only in the outgoing solution propagating in the plus z direction. Since the direction of propagation z is orthogonal to the electric field variation direction, that is x, we say that waves are transverse. That's another important result. Now one can similarly take partial derivative of equation 2 and substitute equation 3, obtaining in free space above solution for the propagating magnetic field now as a wave. Now we have the B field propagation, including B at the edge of the space by the plane, and E field propagation. We just need to relate E and B now. So taking equations 5 and 6 and substituting in equation 3, we get this. So this describes dynamics completely. Now let's see all of this in action. We'll be seeing electric and magnetic field as red and blue lines, vectors respectively, along one d axis in the z direction. So it's like you have like small detectors in line. So as we start to shake the plane with larger amplitude, we see that stronger and stronger fields are created. So pay attention, when current is in positive x direction, By is a negative direction, according to equation 4. E field is pointing to the negative x direction proportional to By, according to equation 7. So finally, if we stop shaking the plane, the wave will continue propagating on its own through empty space. That's the wave equation. Now, of course, we could be shaking at an angle instead of up and down. Then the electric field would be also aligned with the shaking axis. So like this, or like this. This additional degree of freedom, characteristic of transverse waves, is called polarization. Now, the discovery of electromagnetic waves enabled radio, radar, Wi-Fi, but actually electromagnetic spectrum is much larger than that. Just a few months ago, actually, there is this result from astronomical letters. So on the bottom line, you see the electromagnetic spectrum. Note the logarithmic scale. On the top is the observation by the now famous object, black hole M87, with different instruments and magnifications. So we see here that there are instruments imaging this black hole in radio waves, in microwaves, in visible range, in X-rays, gamma rays, and even faster oscillating cosmic rays. This new wavelength is a new window into physics. And if you're sensitive to polarization of the radiation, you get even more information, as you can see on this picture here. Now, conceptually, Maxwell was really important for establishing the concept of field. And here's what Albert Einstein said, quote, "Before Maxwell, people thought of physical reality, insofar it represented events in nature, as material points, whose changes consist only in motions which are subject to total differential equations. Now, after Maxwell, the total physical reality is represented by continuous fields, not mechanically explicable, which are subject to partial differential equations. Now, this change in the conception of the reality is the most profound and the most fruitful that physics has experienced since Newton." Now, with these words, I want to leave you with one slide summary of everything we have done today. So we derived each of these results, and if you multiply divergences with volumes and curls with surfaces, like both sides of equation, you can read equations as it is stated below. We saw that Maxwell introduced new term, displacement current, and this term then couples all equations such that we have electromagnetic waves that propagate through empty space. The waves are transverse to the direction of propagation, hence we have an additional degree of freedom called polarization. And they go at speed of light because visible light is one type of electromagnetic wave. Now finally, we introduced this notation to help you remember terms. More generally, divergence detects sources and sinks, and curls detects loops in any vector field. Thank you very much.